online algorithms. The idea is just simple. No information of future inputs, but still you have to make your decision right now about your action. That is the idea of online algorithms. You already studied one important example, that is linear research. So you are given a linear list. Of length n, then request comes. Request comes something like 51. Okay. Comes like 51. Then you have to search. You have to search item 51 in this list. Okay. Just doing sequential search. So you need to move from here to here. Okay, these are 51 steps. This is your cost. This is your cost. Okay. So what you do, your strategy is to move accessed item to the direction of front. The direction of front. Okay. Your strategy. Your strategy to move the accessed item forward. But the question is how much? This is an interesting problem. But what you can see immediately is if you move the accessed item a little bit, or you don't move the accessed item at all, then that is bad. Because suppose that you don't move accessed item at all. Suppose that you don't make any movement. Then what is the worst input? Worst request is always access. Always require this last item. Then you need n steps. And n steps, and n steps. So you always need n steps. But the optimal algorithm, of course, moves this item to the top for the first input, for the first request. Then after that, the optimal that algorithm doesn't need much steps, just one step for remaining inputs. Remaining request. That's why the competitive ratio becomes bad. The obvious thing is it is bad. It is bad not to move the accessed item. Okay. So now our theorem. So move to front. That's just a simple algorithm. Just you move the accessed item to the top, as much as possible. To the top. To move it top is, of course, the maximum amount. Okay. And this has a competitive ratio of 2.0. So really amazing. It's because it is not very intuitive. If you move the access item to the top, then of course it's good. If you get another request for this item, but it may be possible that you'll never get the request for that item once again. Okay? So I don't know if it's not very obvious why this algorithm is good. But actually you can prove that the competitive ratio of this algorithm is just 2.0. Not amazing, because it's on average, not on average, on average. For any request, the cost of this algorithm is at most 2 times the cost of opt. Okay? So this is a really interesting theorem. Today, we're going to prove that this algorithm is optimal. Now, I'm going to prove that this algorithm is optimal. Meaning, no algorithm has a competitive ratio of better than 2.0. No algorithm, no online algorithm has a competitive ratio of, for example, 1.99. Okay. A proof is again very clever. You can feel that in a moment. Okay, this is the theorem. So what we'd like to prove is that for any algorithm, there is a bad input. There's a bad request, such that that algorithm works not very good, not very well for that input. Okay, that is our strategy. That is our basic idea. So consider any online algorithm A. Then you can consider what we call adversary. Against this algorithm A, kind of an enemy. Okay. We can consider the adversary against this algorithm A, meaning this guy okay. So this guy gives malicious requests to this algorithm A. And this is the basic idea of proof. Okay. So this is the initial list. Yeah, list. Okay, what is a malicious request? What is the malicious? It's obvious. The first request is n. The last one. This is very mean because we need n steps. Okay. Then algorithm A moves this item to the direction of front. So the next is I don't know. Maybe this the last item. Maybe x1, I don't know. Which item is this? But again, request is x1, the last item. Okay, very, very mean, very malicious. Now, so the adversary request is always the last item, the final item. Okay? And xm. Okay? And to assume that m is sufficiently large. So we consider a long sequence of requests. Okay. Then the cost of algorithm A is, of course, m times n. For each request, algorithm A needs n steps, and we have m requests. So the cost is, of course, m times n. Okay, now, consider. Okay, now we consider offline algorithm O, optimal online algorithm O, who knows the whole input in advance. Okay? The question is, what kind of algorithm is O? Is this optimal algorithm? How does this algorithm work? Interestingly, we don't know. We don't know how it works. Because we don't know this input. Okay? Because this input is determined by algorithm A. Right? We don't know this request because this request is determined by algorithm A. And we are now considering any online algorithm A. So we don't know this input. That is why we don't know how the optimal offline algorithm works. However, Okay. We can prove that for any input sequence. So now just forget. Just forget this. Just forget this. For any input sequence, for any input, so just forget algorithm A. You don't have to consider algorithm A at all. Just forget everything. For any input sequence sigma, for any input sequence sigma, there exists some strategy O such that its cost is 1/2 of the cost of A. The cost of A is m times n, and this is 1/2. That means the competitive ratio is at least 2, right? Because the optimal cost is at most 1/2. That means competitive ratio of A is at least 2. Right? Okay. The question is, of course, how we can prove this sentence. Okay. The strategy of algorithm O is quite simple. At the beginning, algorithm O knows that input sequence sigma, then optimal algorithm O computes a best permutation pi of 1 through n. And he or she use this permutation, and so this is the initial permutation. Then he or she changes this permutation to permutation pi. Then after that, he or she doesn't change it at all. So at the beginning, he changes this this sequence to permutation pi, best permutation pi. Then it doesn't touch that permutation after that in the whole course of the algorithm. It's quite simple. That means he doesn't move anything. He always uses that best permutation during the whole course of the algorithm. Okay? It's very simple. Of course, the question is there is a small problem. How can he change the list, the initial list to this permutation pi? Okay, that is not so difficult. So let's just for a while let's forget it. Okay. So suppose that the algorithm O can get the best permutation pi. Okay, and let's consider the cost of A cost of O after that. Okay. Now, let's consider all permutations pi 1, pi 2 through pi t. t is equal to n factorial because the length of the list is n. So let's consider all permutations. Then we can prove that there is a best permutation pi in this permutations. There must be best permutation pi. That is our proof. Okay. Exist the best permutation. Pi alpha. There exists the best permutation pi alpha. Actually, it is interesting. We don't know how to compute this permutation. We don't know how to compute this permutation efficiently. But we can prove that there exists this permutation pi. Why? Okay, it's pretty easy. Now we have pi 1. Okay, it's pi 1. That is just 1, 2 through n. Okay, the first request is n. Maybe, I don't know. The first request might be x. Okay, maybe n. Okay. The next request is x1. x2. Okay. Second permutation pi 2. I don't know. 2, 1. Maybe 2, 1. Third permutation. And so pi alpha. I don't know. Maybe 5, 7. And pi t. So I just wrote all permutations. Okay, t permutations. T is equal to n factorial. We just wrote all permutations. Okay. So the algorithm O, this algorithm O, compute one of these permutations. One of these permutations that should be best for this sequence. Okay, then we don't change. We don't touch. The whole sequence, the same. Okay. So what is cost? The cost is C1. Maybe I don't know. Where is here x1? So this is C2. Oh, I'm sorry, C11, C12, and I don't know, C13. Something strange. Okay, that's fine. C1, N. Maybe there's a mismatch. Okay, C1, 0. C1, 2. Okay, now I don't know. Yeah, and it's here, so C1, C2, 0. C2, 1. C2, 2. And C2, M. C alpha 0, C alpha 1, C alpha 2, C alpha M. CT0, CT1, CT2, and CTM. Okay, the cost. Cost of this permutation is C10 plus CR. Okay, yeah. C11 plus C1M. C20 Okay. This is the cost of the permutation pi 1, cost of permutation pi 2, cost of permutation pi alpha, and the cost of total cost of permutation pi t. Just we look for the minimum cost among these t costs. Okay? So the question is, which is the minimum? Which is the minimum? Suppose that this one is the minimum. The cost of pi alpha is the minimum. Okay? Suppose that this is the minimum. Then what is that value? Then cost O alpha is suppose that this cost I'm sorry something's missing. Okay, O1 okay, suppose that O alpha is the minimum. Then its value is of course at most average, right? This value is the minimum. This value is the minimum among those two things. The minimum means at most average, right? At most average. Then what is average? Average is of course quite easy. C01 plus C11 plus C1M plus C10. Two zero. What is average? Average is, of course, the whole sum of the t values divided by t. Right? The sum of the whole t values divided by t. That is average. Exactly is average. Now, we calculate this value. We calculate the sum of these values. Then this is equal to t times n over 2 plus t times n over 2 plus t times n over 2 Okay. This is all permutations of length n. All permutations of length n. That is just all permutations of length 3. Okay. So this permutation just look like this. Okay. So what is the request? Request is 3. Request 3. What is the cost? What is the sum of the cost? The sum of the cost is, of course, 2 times 6. Okay, this is 3, 2, 3, 2, 1, 1. That means the average, n over 2. In this case, it's n is 3, but it's a little complicated, but the idea is n over 2 times 6. This is the cost. Okay? And exactly the same. Again, this column is, of course, the same. 1, 2, 3. 1, 3, 2, 2, 1, 3. Then request is what? Request is maybe, I don't know, 1. Again, the cost is the same. The sum of the cost is all the same. And the sum of the cost is same. Okay, same. All the same, and the value is 2 times t times this value is 6. In this case, t times n over 2. And just a simple calculation. Then after this is a simple calculation. We have n over 2. We have m n over 2s. We have m n over 2s. So that is exactly m times n divided by 2. We are done. Cost of this alpha, or alpha is at most this value. We are done. As I said, the small problem remains. That means how to make how to make the permutation, how to make the best permutation pi alpha from the initial permutation one initial list. Okay, initial sequential list. We need to make a permutation pi alpha. That is best permutation. Well, you know, we need several steps. We need several steps to make this this list. But if by assuming this value m is, you know, much greater than n, this is not a big problem. Okay. If the value m is much larger than n, then this value, the cost for this initial preparation is not very important. Maybe this is your homework. Yeah, this kind of exercise. Okay, it's not so important. Okay. So we are done. I hope that you can feel that there are many interesting proof techniques for online algorithms. It's really interesting. Yeah, that is one reason why I love online algorithms. Online algorithms is one of my favorite topics. Yeah, there are many interesting proof techniques. Okay. Let's go to the next example. Example 3 is the K-server. The K-server problem is very important. As one of the most important online problems, that is K-server. Because this problem has many applications to scheduling problems like memory maintenance, cache memory maintenance. Okay? The cache memory maintenance is exactly this K-server problem. But today, you know, I'll show you a very basic form of this K-server problem. The problem is a game is played. The game is played over two-dimensional Euclid plane. So we have K-servers, 1, 2, 3. K equals 3. We have 3 servers. So 3 servers are located some positions initially. Then our request is given as a positions, sequence of positions. Our first request is x1, y1 here. This is the first request. Maybe I'll use a different color. This is the first request. Then our action is to move some server to the requested position. We have to move some server to the requested position. For example, you can move this server to here. Okay. So that is your action. What is your choice? Your choice, of course, which server you should move. That is your choice. You can move this server, or this server, or this server. Okay? Why it's important? Because you don't know of course, we have a next request. Next request. For example, here. You have a next request. And again, you have to move some server to the requested point and next request. And this is, of course, online program. That means you don't have any information about the future request. That means this is the first request. Then you don't know where the second request comes. Okay. Probably, you come across small cars in the town. This is emergency for your lock system. So if you lock your key inside your apartment, or you lock your key, you left your key inside your car or inside your apartment, then it's a kind of emergency. You don't have your key, but you have to unlock your apartment. Then the final, your final choice is to call this, it's a emergency company. Then this guy comes to apartment. Then they are very technical. Okay, they can unlock your apartment for you. This is an emergency car. Exactly this problem. So in Kyoto, maybe one company has maybe 10 or 15 this kind of small cars. Then if they get a request, then they have some kind of a request. They send some request to some car to move to the point, to move to the position. Okay, exactly this problem. We have an initial location of 3 cars. Then this is Kyoto University. This is maybe I don't know, maybe Kyoto Station, near Kyoto Station, so near Fushimi. So they have to send one of their cars to the requested position. Of course, so formally speaking, request input is initial position of k servers and request. Sequence of requests x1, y1, x2, y2, and so on and so forth. The action, your action is to move okay. For ith request xi, yi, you have to move one of the servers to the requested position. That is your action. Of course, your choice, your strategy is which server to be moved. That is your strategy. Cost. Your cost is, of course, the total moving distance, the total distance to move the servers. That is the cost. Your goal is to minimize this cost, of course. This is a formal description of the problem. Is there any question? Is it clear? It should be clear. Okay? Okay, so then what is your algorithm? Just consider. What is your algorithm? Okay, what is your algorithm? Let's see. Okay. Now, this initial position with servers. Suppose that the first request comes here. This is server 1, server 2, server 3. So what is the algorithm? Which server would you move? 2. Exactly. 2 is closest. Okay, so this is the most natural algorithm. Exactly. So, the natural algorithm the most natural algorithm is called greedy. That means moving the closest server. Moving the server which is closest to the requested point. That is the most natural algorithm. The question is if this algorithm is good or not. Using our comparative analysis, this algorithm is not very good. Why? Okay, so you moved this guy to the requested point. But the adversary chooses the next request where? Exactly, here. You know everything. Then again, his algorithm had to move this server to here. And what is next request? Again here. So you have, he has to move the server always. But if you know the request comes this point and this point repeatedly, then what would you do? Of course, for the first request, we move this guy to here. Then after that, we don't have to move any server at all. That is the essence of online algorithms. Okay? So we always consider the worst case. That means that we have to consider good algorithm, which works pretty well for the worst case. That is what our good algorithms. Okay? So, unfortunately, this greedy, its competitive ratio becomes infinity. Okay. Now, I'll show you good algorithm. Show you good algorithm. Our algorithm is called greedy. No. Our algorithm is called DC. DC stands for double coverage. Why it's called double coverage, I'll show you in a moment. You can see in a moment. Okay. So, here, I'll show you a simpler version. Namely, it's a 1D. Request one-dimensional version. Of course, usually this game is played on a two-dimensional Euclid space, but here I'll show you a simpler version. That is a one-dimensional version, meaning all requests comes on a line. Right. That is one-dimensional version of the problem. Why? Because this is much simpler. Extension is possible. Extension to the two-dimensional plane is possible, but not very easy. We need much more work. So I have only 30 minutes to go. I'll explain using one-dimensional version. Okay. So, and now one-dimensional, you have now line. No. We have a line, and server is located like this. And the request comes. For example, here, the request. Okay. And you have to move some server. To the requested point position. Okay. Now, DC has two cases. This is very simple. DC is very simple. Case 1. Okay, case 1 is a request comes outside. Outside of the range of the current servers. Okay, this is the current servers. And request comes outside of the current servers. Okay, do you understand? Is it clear? Outside, not inside. Okay, outside. Then the DC moves the closest server. It's greedy. Greedy move. Okay, the first case is if the request comes outside the server region, then just move the closest server. Just move the closest server. This is one case. And the other case, of course, that the request comes inside. Request comes inside. Then, it's, our server movement is a little bit interesting. We move two servers by the same distance. What does it mean? It means we move two servers like that. Well, it's against the rule. Usually, we can move only one server at one time. Well, okay, maybe we can remove that rule, or even if we still, stay on the rule, it is possible. Because, we don't have to move this guy, because this guy comes first to the requested point, then actually, we don't have to move this guy. So what you do is just a program. Within your program, just simulation. You can do the simulation. And when you have to move this guy actually, okay, then you can do that. So, okay, this is not a big problem. So now, suppose that we can move two servers at the same time. Okay, of course, our cost is the sum. Our cost is the sum of these distances. Of course. Okay, this is our DC. Always. Now, okay. Competitive ratio of DC is at most K. K is, of course, the K of K server. In this case, we have 1, 2, 3, 4, 5. So if the number of servers is 5, then its competitive ratio is at most 5. Okay. Using the remaining time, I'm going to prove this theorem. Okay. We again use the proof strategy is completely the same as before. As before means the linear list. The case of linear list. Use a amortized cost. Just remember that our amortized cost for linear okay. Our cost is K plus so this is our previous cost. Okay. The amortized cost at step J is a real cost. Real cost means the cost of the algorithm plus this value minus this value. What is the inverse? Inverse is a number of pairs. The number of pairs which are different between optlist and algorithm list. Okay. So we need to come up with some kind of a parameter, some kind of value, some kind of a measure to show the difference between server and opt. No. The optimal opt and the algorithm. Okay. With the same idea, so use okay. I don't know why I changed the subscript from J to I, but anyway, it's not so important. So this is amortized cost, AI. Just general speaking, okay, we use amortized cost AI at step I. Step I. That is the real cost of the algorithm at step I plus something. I'll show you in a moment what kind of value is this. Okay. Then our goal is to prove if we can prove this amortized cost AI is at most C times opt. Then we are done. Then the complete ratio of algorithm A is at most C. Why? Because it's a okay. If you can prove this inequality, then you just sum up the whole cost of this side. Then this side and those guys just cancels. This is what we exactly did last time. So our goal is to prove this. Then we are done. So amortized cost is amortized cost is what? Amortized cost S of I is equal to yes. Okay. Algo I is, of course, the cost of our algorithm DC at step I, and I'll show you what this function, what this phi I plus phi. Okay. So define phi as define phi like this. Here, M is matching. Meaning, so M is a matching. Meaning, suppose that this is a distribution of the servers. This is a distribution of servers. The distribution of servers hopped, and this is a distribution of DC. Okay. Just notice, there is at least one server whose position is the same. In this case, this position is the same. There's at least one server whose position is the same. Why? Because this is a last request. Right? This is a last request. So at least one position is the same. But anyway, M is matching. So here. M is equal to M1 plus M2 plus M3 plus M4. What's the value? Just a matching. No, kind of total difference. Total difference between opt and DC. Okay, this is M. Okay. I'm running out of time. Okay. Now, sigma DC. Okay. Sigma DC is the sum of all distances between two servers on DC. That means this distance Okay. So the sum of all those red distances is sigma dc. Okay? So the phi is the sum of those two values. Those two values. Okay. Now let's start our analysis. Let's start our analysis. Step I. Step I. Okay. Opt. Okay. Suppose that request comes here, then and opt with this guy. This is opt. Suppose that at step I, request comes here, and opt moves this server to the requested point. Then, what is the difference of phi? What is the difference of phi? What's the difference of phi? Can you see here? Okay. What is the difference? What is the increase of phi? Okay, that increases at most kdi. At most kdi. Why? Now just look at this. Look at this. The situation is just this server moves here. Moves here. Then of course this matching value m1 increases di. Okay. Then what is this value? K times di. K times di. So phi increases at most k times di. Once again, just opt moves this guy to here by di. Then this value increases by di. Okay. Then this phi increases by k times di. Other value doesn't change. Other values don't change at all. Now, DC. Okay. DC had two cases. Case 1, okay. Case 1 is outside case. Outside case. Then the algorithm moves the closest server. This is SI. Then M. In this case, I don't know of the distribution, but maybe something like that. Something like this is of the distribution. Then, if this guy moves here, then m increases si. Okay, so because this distance becomes less. Okay, so m increases si. M increases si. What is the sigma dc? Sigma dc increases the distance of this and this increases by si. That means increases k minus I si, right? This is okay. This guy moves here. This guy moves by si. Then all those three costs increases by si. So increases k minus 1 si. Okay. Then what is this phi? Phi. M increases psi, and this k minus 1 increases. Then phi decreases si. Something strange. Yes. This increase, this Yes. While increase decrease is a little bit complicated. It's a kind of a way of thinking. Yeah, but this is correct. Okay. Now, DC case 2 is now here. The amount of movement of DC is SI. That means SI over 2 from here to here, and S over 2 from here to here. Okay. Then M does not change. Why? Because it's a here. It's a I don't know. Maybe this. Then this M increases, but okay, so the idea is one M is increasing, but another M decreasing. So does not change. It's not so easy to write. What is the best way? Yeah. Okay. So something like that. Then this M decreases, but this M increases. by the same amount. This m decreases because this guy comes here, but this m increases, but this m decreases by the same amount. So m does not change. M does not change. And sigma dc decreases Si. It's obvious. It's obvious. You know, this amount, this distance. This distance just decreases by Si. The relation against the other guys just cancels. Okay, so this guy decreases S over 2, but increases S over 2. So all cancels. So only between two guys, only for those two guys, decreases by Si. So, what? Okay. So, in both cases, phi decreases by Si. That means this value is equal to what? Oops, something different, interesting. Oh, I'm sorry. This is very bad. This is very bad. Sorry. Oh. Yeah, this is okay. Sorry, I messed up. Okay. Delta phi increases at most KDI by movement of opt. This guy. And decreases Si by the movement of DC. So yeah. So this is correct. In both cases, the amount of phi decreases by SI, by the movement over DC. Okay, so this is correct. And this is just a simple calculation. A simple calculation, and exactly AI is at most k times DI. DI is the cost of opt. That means we are done. We are done. The cost of algorithm at step I is at most c times, in this case, k times the cost of opt. That is DI. Okay, so we are done. The K-server is very important, and once again, we can prove its competitive ratio by using amortized cost. So maybe it's a little bit complicated, but it's not so difficult. Just look at your note again, then it's not so difficult to understand this proof. Okay, so we are done. Maybe next week I'm going to the new topic. That is what? I don't remember what is our next topic. But maybe we are moving to a new topic next week. Okay, so see you next week.